This is an example of a suspension bridge. And this is a cable-stayed bridge, and an arch bridge, a beam bridge, cantilever bridge, a movable bridge, a floating bridge. There are a lot of different kinds of bridges, but they all serve the same function.
So a bridge is a structure that's designed to be able to carry movable loads from one side to another. It needs to be able to traverse or span a distance, whether it's caused by a body of water or another road that's beneath it.
This is the guy who decides what kind of bridges to make.
My name is Dr. Nehemiah Mabry. I am a structural engineer and educator.
And what is a structural engineer?
A structural engineer is an engineer that specializes in designing structures or any types of stable bodies that's able to resist loads or weights of any kind.
So why are there so many different types of bridges?
Bridges are designed from the top down, but they're built from the ground up. And so we as engineers began to think how much load or what type of weight does this bridge need to carry, and how would this deck then transfer that weight, whether it's a moving truck or a resting parapet or concrete divider.
How do you decide what kind of bridge to build?
Right, so there's a couple of things we look at when we want to design a bridge. So you look at skew angle, you're going to look at stationing or work points. You're also going to look at what we call a typical section, which is what is it going to look like if once we slice this bridge in half? What do we want that typical section to look like? And then from there, once we get that, it's a matter of calculating the loads that the various lengths of girders or various length of materials that are necessary. We're going to also look at the material that we want to use to then be able to produce that typical section that we desire. There are primarily two main forces that each component, each member of a bridge is going to experience. Is either a tension force or a compression force. A tension force is basically a force that will attempt to try and stretch the member or stretch the component of the bridge. And a compression force is a force that will attempt to shrink the member or the component of the bridge. And so those are the two main forces that any member of the bridge will have to experience. Some members will have to experience both at the same time. For instance, if you have a beam, now a beam is a long member that is meant to span from one support to the other support. In many typical cases, the beams are supporting the loads transferred from the deck. Well, in the middle of the span, these beams are often bending or experiencing stresses or a force that causes a bend. Well, in this case, you're going to have the bottom of the beam that's going to be tempted to be stretched. That is a tension force. However, the top of the beam, as it bends, is going to be experiencing a compression force because at the top, it's going to be shrinking. An example of a component experiencing maybe just compression would be the columns. This is a part of the substructure, which is connected directly to the foundation. As loads from the beam rest on the columns are going to be experiencing compression, more specifically axial compression along the length of the column. Another case where tension may be the only thing, given a case of a suspension bridge. These are bridges where you see a draping cord or cable going from one support to the other, and then hanging from those draping cables are additional cables that are then attached to the deck to hold up the deck. Well, these particular cables are experiencing pure tension because it is experiencing a force that is stretching those cables.
So, here's a bunch of different bridge types.
Suspension bridges, they are typically supports or towers connected by a draping cable. And from those draping cables on both sides of the bridge, there are vertical cables that then connect to that draping cable down to the deck. And the weight of the deck is then resisted by those vertical cables and tension connected to the draping cables that then transfer the load to these towers.
What's the best example of a suspension bridge?
The most recognizable example, particularly in the United States, is the Golden Gate Bridge. The Golden Gate Bridge is that bright red, that beautiful landmark out west that has these two very strong draping cables going from the north to the south tower. And from those cables, they're typically made of steel wires wound and compacted together, which make them very, very, very strong in tension, draping vertically from those main cables down to the deck. What's so great about this suspension bridge is that it's in a region that is known to experience earthquake. Being that they are supported by cables for the most part, there is the ability for bridges like this to be able to have some sort of give and not be so stiff and be able to move even if the ground shakes without severely damaging itself. The north and south ends of a suspension bridge, particularly the Golden Gate Bridge, are referred to as piers. And these piers act as the substructure which needs to resist those forces that is being applied to it by these main cables. And so these big piers need to be extremely reliable because they are essentially resisting half of the bridge's weight.
What's another type of bridge?
Another similar or cousin I like to think of to the suspension bridge is a cable stayed bridge. In this case, they're similar in that there are towers, primary supports that then connect to the ground. But instead of having two main draping cables, the cables are then attached directly from those towers, from those piers to the deck. Each side of the tower sort of acts as a counterweight to the other side. And so this is not only helpful in the way that the bridge remains in equilibrium, but this is also something that many have used to their advantage throughout construction of those bridges as well, by holding things in place as things are being built. What it allows you to do is use cables to then act as a resisting force to the suspended or hanging deck. Because the deck in and of itself is not required to have anything beneath it, your cables are able to go much, much longer than you could fabricate anything else to serve as a superstructure.
So, cable stayed would be really useful for long or tall bridges.
Yes, so the Milan Viaduct is actually the tallest bridge in the world, being that you have each piers that is about the height of the Eiffel Tower itself. And from it, you have your cables that are keeping the deck in place, making it a very aesthetically appealing bridge, but also using the counterweights of both sides to be able to have a much longer span in between piers than you would with any other bridge type. It's only but so long you can design a plank or a girder. And so because you don't want to have so many supports, also when you're traversing or you're building a bridge across a large body of water, the energy and the effort it takes to drill piers or piles down beneath the surface of the water and to build these supports makes it more of an incentive to have less supports, right? And because we want less supports, we're then going to consider a bridge type that can allow us to have longer spans. Hence the suspension bridges, and even more so the cable stayed bridges becomes an attractive option. Not to mention it just looks cool.
So that means some cable stayed bridges might have only one support.
Right, exactly. So the Langkawi Sky Bridge is a curved pedestrian bridge. It's just beautiful. It has the aesthetic value right there. It's an interesting design challenge when you look at how can we put this man-made structure in this place, but yet at the same time preserve the natural beauty of that environment. So it is then advantageous to then say, how can we have the minimal amount of piers, in this case, even one pier, positioned and act as a support for the entire bridge, which is why this truss pier is singularly located and then attached to cables, 8 cables to be exact, that are necessary to support the deck in various points, thus providing the support needed to support the traffic.
Can you combine these different bridge types?
Yes, so the Brooklyn Bridge is a good example of a hybrid between a suspension bridge as well as a cable stayed bridge. So you have your very, very large towers, your pillars, your piers that have existed for a very, very long time that have these draped cables from one to the other. From these draped cables, there are vertical cables that are attached to the deck, as you would see in any other suspension bridge. But if you look very, very closely, you will also see that some cables are at a diagonal. They're also attached from the deck directly to these tower piers, which makes it more of a hybrid between your suspension bridge as well as your cable stayed bridge. The cables of the Brooklyn Bridge are comprised of 19 strands that are then bundled together, and then each of these are composed of about 278 wires per strand, and together they actually produce a much stronger tension resistance than if you just had a single solid strand. So those towers on the Brooklyn Bridge are stone towers as well, using limestone, granite, and other rocks that have proven to be able to stand the test of time because of their durability and strength and compression.
What is our third bridge type?
Arch bridges are primarily resisting the load and axial compression along the arc. Within arch bridges themselves, you could have a spandrel arch bridge where the deck is above the arch, or there are cases where the arch is elevated and the deck is actually through the arch. And so we call that a through arch bridge. Particularly stone bridges stand the test of time because stones are a natural material. And so using a material that has already went through the years of weathering, countless years of reformation, and really been able to remain what it is over millennia. So I think that's one of the reasons why stone bridges and even arch stone bridges was able to stand the test of time, because it's simply asking of the material what the material has already been doing for many, many, many years. When it's designed appropriately and the geometry is nailed, you can pretty much have a bridge that is invincible.
What's a good example of an ancient arch that's still standing today?
So the aqueduct is another example of a stone arch bridge. Here we have a series of stone arcs that allow the force to be transferred actually throughout the arc. These smaller arches then, of course, transfer the load to the bigger arches. It takes advantage of the opportunity of breaking up the spans such that so much isn't required of a single arch. It's also redistributing the load across the smaller arches so that as they're transferred upon the bigger arches, the larger arches can then act as piers that are spaced further out apart, giving greater spans.
What then is a truss bridge?
A truss is a structural type that is comprised of several different elements. The triangular shapes are necessary such that each element of the truss is experiencing a pure tension or a pure compression.
Can you give us an example?
So the City Harbor Bridge employs two truss in the shape of an arc, and it also is the type of arc that we refer to as a through arc bridge, such that the deck is not above the arc, but is in line or beneath the apex of the arc. There are also vertical struts that then connect from the truss arcs that are to support the deck through tension. This aligns with the use of the elements within the truss as well, which are also designed and put in place to be able to only experience purely axial forces, whether it be in compression or in tension.
Aren't truss bridges used by the military for rapid deployment?
Absolutely. The Bailey Bridge is sort of a military bridge that is prefabricated, pre-built away from the site that it is to be put in place to transfer vehicular or pedestrian traffic. It really came out of the need for military units to be able to quickly build a bridge, for it to be light enough for them to carry with them as they move from one place to the other. And it's sort of like an erector set, piece by piece, prefabricated, put together, and can be constructed without the use of heavy machinery, without the use of a crane or any pile drivers of any sort.
What type of bridge is this?
So a cantilever is a structure that is supported on one end, where there is a fixed side or support, whether beams or other types of support members that are resisting the rotation of the deck. And so cantilever is incredibly important to make sure that the fixed end is strong enough and that the flexing extended member has the ability to resist the tension on the top and the compression on the bottom. Perhaps the longest cantilever bridge is the Ponte Quebec Bridge there in Quebec, Canada. Steel, unlike concrete, is extremely strong in tension. It can resist forces that attempt to stretch it. And so while we are making beams that perhaps are going to experience a lot of bending, we want something that can resist the compression at the top and the tension at the bottom, or vice versa, depending on how it's expected to bend.
So how do you make a material that resists heavy loads?
We've gotten very sophisticated in how we are anticipating the types of loads that these beams are going to experience. And so instead of just simply putting steel inside of the concrete so that you have that reinforced composition, there's another type that we call pre-stressed concrete. We take the steel before we bring the concrete in and we stretch out the steel. And while in that tension position, we then pour the concrete around it and create a beam with the tension steel. And after that concrete has hardened, then we release the tension off of that steel such that now the steel wants to then retract back to its original position. But because it now has concrete around it, it is actually pre-stressing before it experiencing any load. It's already applying a stress load on the concrete. And so now you have a bow where the concrete or the beam is going to want to naturally, without any load on it, bow up a little bit. And so that's a way to sort of anticipate the fact that when loads go and we put these beams in place, the loads are going to want to make the beam deflect downward. But because we put what we call camber, we put camber into this pre-stressed beam, we sometimes are able to achieve no deflection at all at the beginning of installation.
What other bridge types are there?
When we're talking about plank bridges, then those planks are acting as beams. And so they have to resist what we call bending moment. And so a bending moment is what causes these beams, in this case, to experience both tension and compression. Compression being at the top as it begins to bend, and tension being at the bottom as it begins to deflect. So the UBM bridge is the largest wooden footbridge in the world. It has upwards of 1,000 wooden pillars that have been driven throughout the water along the length of the bridge. It has approach spans that were originally made of stone or brick, but had then also been replaced by wood. Over time, the weathering and the deterioration of certain pillars have been replaced with concrete, but nevertheless, this is primarily an entirely constructed wood bridge that offers amazing views there in Miramar. Along the length of this bridge, there are 4 wooden pavilions at equal distance. I don't know, you'll call them maybe checkpoints along the length of the bridge, being that it's so long.
So what about this bridge in Enoshima, Japan? What type is this?
This bridge is another pure example of a bridge type. There aren't separate members that you're connecting and transferring load with, but it can almost be looked at as a frame in and of itself that put in place. And you look at it, and that's the money shot right there, right? Looking at the super steep incline and decline that it has when you're approaching the bridge. That shot definitely, it helps exaggerate the steepness of the grade. However, it is a lot steeper than your typical bridge on its vertical curve, as we call it. It has about 5%, 6% slope, which is quite the slope for any passenger or vehicle driver may typically drive on. But it's necessary because instead of being a movable bridge, they decided to make it high enough with enough vertical clearance such that the ships can then pass there in Japan right underneath it without any needs of actuators or mechanical devices to be able to move it. Movable bridges are things that we see that are designed to be able to not only transfer the load sturdily, continuously using a deck that connects across the chasm, but it's also designed by some mechanical powered devices to be able to move and to lift up such that the waterway that is traversing can allow the passage of boats or any other vessels that need to pass by. It can then also be lowered back in place so that the loads can continue to travel across it.
Let's hear an example.
So the Somerset Bridge is a very, very short timber bridge to be able to cover a passageway in Bermuda that connects Somerset to Warwick, Bermuda, and it's a movable bridge as well. This bridge doesn't need to be completely moved out of the way. There aren't big ship or water vessels that are passing through. In fact, this movable bridge is operated by hand, unlike other movable bridges which may use hydraulics or other mechanical means. It's just hand crank bridges that allows the deck to open up just perhaps 2 or 3 feet, just wide enough for a mast of a small boat to be able to pass through.
What about a bigger example?
Okay, yeah, I got you. Gateshead Millennial Bridge. This bridge is actually a pedestrian bridge, not meant to transfer any vehicle traffic, but walkers, joggers, cyclists are able to travel that curved outer semicircle of the bridge. It's amazing because it has sort of that eye look. It's referred to as the winking eye as a nickname. Just incredible, just marvel. Particularly when it first went up, it was one of the first of its kinds that we ever seen like that. Instead of actually moving and separating 2 components of the bridge, it is shaped in a way such that the semicircles are able to rotate, and when it is in an upright position, it then creates enough vertical clearance for ships and sea vessels to then pass underneath, and then it's simply rotated back into its place.
What about this sci-fi looking bridge?
The rolling bridge, it's pretty cool. Looks like a little roly-poly bridge. And what's interesting about this bridge is that, as in a lot of movable bridges, this has several joints throughout and triangular sections such that it is able to curl up upon itself with multiple bending locations throughout the length of the bridge. So as it curls up, using the power of hydraulics, being a system that employs the pressure of fluids, it's able to then, at its size, be deployed very quickly, rolled up, put back down, again, nice and neatly, triangular segments, fold on top of each other, and then roll back out, just as easy as you would see a roly-poly do it.
Is there one bridge that puts a bunch of these examples together?
The tower bridge is another kind of hybrid bridge. It's a suspension bridge, and then it's also a movable bridge in the middle. On the outsides of the towers, there are suspension cables vertically supporting the deck. But then there is a walkway bridge at the top of the two towers. Beneath there is a drawbridge that lifts up, allowing the passage of ships. But what's interesting about the tower bridge is that there is also a walkway bridge at the top, which in and of itself acts as a connecting member between the two towers. Because the outsides of the towers are suspension bridges, they are experiencing sort of a pulling force that's attempting to pull them apart. Therefore, the walkway that is connected at the top is acting as a connecting member that's experiencing tension itself, keeping the top of the towers also aligned and in place.
What is the same about all these different bridges?
All of these different types of bridges are essentially doing the same thing. They're carrying load and they're transferring it to the ground. They're just accomplishing it in slightly different ways.
So how do you make sure a bridge stays up for a very long time?
A lot of infrastructure that has been built years ago, expiring, for lack of a better word, around the same time, causes decision makers to have to determine what will we replace entirely and what can we afford to just simply repair. It's not uncommon for bridges to be designed with what we call a 50-year design life cycle. Bridges incorporate a lot of reliability measures, which determine with a high reliability, this bridge will be safe for this amount of time, say 50 years. That doesn't mean that this bridge can no longer perform its function after that design life. However, this is just the highest interval of confidence for which that structure can be designed. You may see in our country, particularly in countries that had large, massive infrastructure projects 50 or so years ago, now at a point where a lot of our heavily used bridges and structures are requiring frequent maintenance. There needs to be a more frequent inspection cycle. There needs to be perhaps some modifications, removal of the concrete that has spalled off or deteriorated or crumbled and replaced with something more durable, such as weather protected steel, which we have, or epoxy coated deck. And so there are rehabilitation efforts that can just as well reduce or restore the ability of the bridge as opposed to just tearing it down. Perhaps there may be cases where an engineer may go and inspect, they analyze, they look at how it may have deteriorated or fatigued over its life cycle, and they won't recommend that it be torn down, but they may recommend that it be posted, and that instead of carrying a certain amount of load, now it be determined that it can only carry a fraction of that load and continue to then function safely for the public. Restoring urban infrastructure is a huge issue because of the fact that the uses increase at such a higher rate. And that's why in New York, a lot of the bridges, the age of the bridges, as well as the levels of use that they experience, require more frequent intervals of repair, maintenance, inspection for the public. We have a high number, an unacceptable number, of either structurally deficient or functionally obsolete bridges, which is why there has been widespread support for the restoration and improvement of our nation's infrastructure. So the choice is either preservation and repair or completely new construction.
My name is Charlie Lewis, and I am a structural engineer with the design firm Stewart. We are located here in Raleigh, but we also have offices in Durham, Charlotte, and Columbia, South Carolina. In addition to structural engineering, we also provide civil engineering services, transportation engineering, geotechnical engineering, landscape architecture, sports and events planning, and surveying. Those are our core services. We do a few other things, but what I do myself is structural engineering. You did just hear Dr. Mabry talk about some of the bridge types and some of the forces involved in those bridges that you'll see around the world. But what I like to do is spend a few minutes telling you about some of the same types of bridges that you can see right here in and around North Carolina. And the first of these bridges that I'd like to tell you about is the Arthur Ravenel Jr. Bridge, which is a cable-stayed bridge in Charleston, South Carolina. It spans over the Cooper River Bridge, and Stewart was lucky enough to be involved in this bridge a couple of decades ago. We started the design of this in around 2000, 2001. We did not design the main span. We designed one of the approach spans, but if I do have to brag, it's that you can't get onto the bridge without crossing over our little piece of it that we designed. There were several design firms involved in this. It takes a big effort to design a bridge like this, just the amount of planning and the number of people and the number of different factors you got to consider. It just takes a whole lot of folks. So we were lucky enough to be one of those. So this is a cable-stayed bridge, like I said, and it spans about 1,500 feet. That's the main span where it spans over the channel. But the bridge as a whole, from where it leaves one bank of the river to where it touches down to the other, is about 13,000 feet, which is about 4 kilometers. So pretty impressive bridge. At the time that we designed it, it was the first longest bridge in the Western Hemisphere. I think now it's the third, because people are building bigger, longer things all the time. But yeah, the time we built it, it was the longest cable-stayed bridge in North America and I believe the Western Hemisphere. The main towers of this bridge are 575 feet tall. For reference, that is taller than the tallest building in Raleigh. So it's altogether pretty impressive. There is an elevator in at least one of the towers. I think it may be in both the towers, but when this was being built, we did get to ride up in the elevator that goes up to the top, and yes, it kind of takes the slant, so it's kind of an odd feeling to ride in an elevator that doesn't go straight up, but straight and off to the side. So anyways, pretty cool to go up there and stand on the top of that and look out over the river. But the forces of this bridge are carried from the deck. They go into these massive cables that carry the tension of the bridge up into the main tower. The main tower is all made of post-tension concrete. So there's a whole lot of rebar, a whole lot of post-tensioning cables in this. And those forces carry down through compression into the base of the towers that you see down here. And they go into the riverbed, and the foundations of these are massive concrete elements that go about 100 feet into the mud that's below there. And there's really nothing but mud below these things. The reason for this bridge is that the shipping channel to the left of the image you see here needed to get larger boats there. And the two bridges that you see off here on the right, those are cantilever truss bridges. So you couldn't get to you couldn't get the largest boats under these bridges over to where they needed to deliver their cargo. So they had to take these bridges out. These bridges were also pretty dated. They needed a lot of maintenance. So they were going to have to be replaced anyways. So what was decided to be done was to replace it with a much higher bridge that could allow larger boats through here. So these bridges were demoed. They took them out to sea and they made them into artificial reefs, or places where fish could swim around and nest and reproduce, that sort of thing. So next bridge is the Reedy Creek Pedestrian Bridge, which is located in Raleigh. It's a truss bridge that crosses over I-440, the Beltline. On the far side of the picture here, that goes over to the grounds of the Art Museum. And on the foreground, that crosses over towards Meredith College. So the total length of this bridge is about 660 feet. So it's 3 main spans, and these are just massive truss bridges. And the top of the bridge there, as it crosses over the highway, is about 55 feet up in the air. Some of you may have been over this bridge, but it's a pretty impressive sight too. Not as impressive as the Cooper River Bridge, but nonetheless, for a local bridge, it is the longest pedestrian bridge in Raleigh. So go check it out. It's right here, real easy to see. This next bridge, the American Tobacco Trail, this is a really, really cool bridge. Pretty elegant, very, very slim. You can see there's just a minimal amount of structure. And the structure that's there, though, is this main steel tube that goes from side to side. There's 2 of them. And then the top of that is the concrete deck. This concrete deck is only about 9 inches thick, and you would call this thing a composite arch bridge. The bottom is the arch piece, and the top is concrete. The two act together to create this composite structure. The main span is about 260 feet, 268 feet from end to end. And the top of this bridge is the reinforced concrete that pushes down into the compression member, which is this arch. But the really impressive thing about this bridge is it's only 9 inches thick, so it looks like this very thin ribbon of concrete. And the way that works is through these very high tension cables that run through the concrete. So after the concrete is poured, they put about 30,000 pounds of force into each of these cables, which puts all this compression force into the concrete. Concrete is pretty weak in tension, so you want to put extra compression into it so that the tension really never has a chance to develop. This next one, though, is my baby. This is the Skycrest Bridge that carries the lower Deuce Greenway through Raleigh. It's a suspension bridge, and the main span of this is 270 feet, and that is from one side of the river to the other. It's kind of tough to see here in this picture, but this concrete element you see here is the abutment on one side, and the far end is the other abutment. So end to end is, again, 270 feet. The bridge is about 12 feet wide, and the way the forces are transferred through here is through tension. These cables can really only take tension. If you try to put compression into these cables, they'd buckle. Just like if you got a piece of rope and you try to push a piece of rope together, it's gonna collapse. It's gonna buckle. So, anyways, these cables take all the tension, and these cables were manufactured in Germany, put on a boat, shipped over here. Took a couple months from the time they left the factory in Germany to get over to Raleigh. The force of the bridge is carried in tension through these vertical cables into the main span cable, which then goes into the tower, and the tower then transfers that compression force into the abutments. And the reason we chose a suspension bridge is that where this thing is, it's back in the woods, not easy to get to, and not easy to get any construction traffic to. So the one thing that we came up with is a suspension bridge that can be built with pretty light components, individual members. A truss bridge was possible, but to get a truss bridge out there would have taken a lot of effort, would have taken a lot of clearing, a lot of heavy equipment to get it back there. So this was the idea that we had, is to try to span it with something lighter. When bid time came through the contractors, this was the cheapest way to build it. So even though truss bridges are usually the most efficient way to do things, just the fact that it was hard to get those materials back in here made the suspension bridge cheaper. So anyways, this was the low bid on the job, was the contractor that could build the suspension bridge you see here. So with that, I'm going to sign off here, but I'm going to turn you over to my colleague, Brian Covington, who's going to tell you about a bridge exercise we're going to have you do. But in the meantime, here's my contact information. If you have any questions about bridge design, about bridge construction, any of the slides you've seen here, I'd be happy to help. So thank you for your time.
Hey guys, Brian here. I'm glad you had a chance to look over some of those bridges with Charlie. Those are some local ones that I hope are familiar to a lot of you, bridges that we all use in our everyday experience. Now I want to dig into tonight's activity. In tonight's activity, you are tasked with spanning this distance across the valley where this train track runs through with any one of the bridge types that we reviewed so far. What you'll want to do is you'll want to establish first where your pier points are going to be, what your span length is between those pier points, and then make a selection from the bridge types here to which one you want to use. Your abutments are at your work point 2 and your work point 1. I want to show you an example of a bridge that we at Stewart designed about 10 years ago. Some of you may be familiar with. I think Charlie went over it in the video already. I want to talk to you a little bit about how we went through the same process in our plan set. So this is the Neuse River Greenway Bridge. And what you'll see is it is a suspension bridge, as Charlie talked about already, and it is resisted by our primary pier elements, the ends, which are in compression, and our primary tensional elements, which are those smiling cables. Things that smile are in tension, things that frown are in compression. Simple way to think about it. So here's the side view of that bridge. And what you'll see here, again, are those primary tension cables running in that smile shape across the bridge span. And you've got the deck itself down here. We know that because this cable is carrying the dead weight of this bridge below, and that it is holding that up with these vertical cables, that cable, that primary cable, is in tension because it is carrying all of this hung weight. So we represent that with a couple of tension arrows, red arrows. From those primary cables, we are hanging our vertical cables. Those vertical cables come down like this. They are what is holding up the bridge deck below. So because they are holding up that bridge deck below, they are also in tension. Now, the bridge deck itself, we talked about that already, how in any beam element, you're going to have tension developing in the bottom of the beam, and you're going to have compression developing in the top of the beam. We're going to represent our tension by our red arrows and our T's, and we're going to represent our compression with blue arrows. As we spoke about just a minute ago, when all that tension force comes back up to these piers, it has to go somewhere. What we've developed in our design is a counterweight that's tied back into the bank here. That counterweight has a cable that proceeds to the top of this pier to receive all of this tension. So this tension force here becomes another tension force here as it passes over the top of the vertical pier. The same thing happens on this side. That tension force and this tension force on either side are transferred into the ground at the counterpoints. We typically develop this with a large mass of concrete, rock anchorage into that concrete and into the bedrock below, or weathered rock below, and micropiles, as you've seen here. Ultimately, they are critical elements because they are what keeps this bridge in tension. Now, the vertical piers, here and here, have to resist all of that tension force running over the top of them, right? All that goes this way. And what that develops is an equal and opposite reaction by Newton's law, which says that this must therefore be in compression because it has to push back against all of that downward force that is developed by that tension running over top of the pier. Laying out tension elements, your primary tension elements, your secondary tension elements, and your equivalent compression elements in the bridge. As part of your activity, you need to do this for your bridge that you choose over the railroad track span, and you need to develop a typical cross section for that bridge. Now, a typical cross section, we're looking at what's going on through the middle. So if I was to cut a section right through the middle of the bridge, right here, through the bridge deck, looking this way across the deck, what would I see? I would see this. Here you see your concrete deck where the people and the cars and the bikes live. And we have our steel superstructure that supports that concrete deck. And then you see here the vertical cables that are coming down from above, right here and here. Those vertical cables are what run up to the suspension. You also have your handrail element here, and a handrail element here. Here you have your clear span, 13 feet from outside of concrete to outside of concrete, and 12 feet clear from a handrail to handrail. So, back to your activity. First step, measure that span once you've determined where your piers are and where your abutments are. If you want no piers, you can do that too. You just need to pick a bridge that can handle that long span. Then you need to determine which bridge type you're going to use. You need to define which members are in tension and which members are in compression. And then lastly, you need to draw that section that we just looked at to the middle of your model. All right, guys, enjoy.